The most recent imagery captured by the James Webb Space Telescope has left researchers in awe, revealing the universe in ways that were once thought to be beyond our grasp. These images are not only enhancing our understanding of the cosmos, but are also uncovering perplexing phenomena that imply our current knowledge may not be adequate to grasp the early formation of the universe fully. Established theories about the universe's origins are now facing challenges, pushing the scientific community to explore alternative hypotheses regarding its inception. This raises a pivotal question. How did the universe come into existence? And why are these groundbreaking discoveries presenting difficulties for even the most seasoned experts in space science? This calls for a more thorough investigation into the true nature of the Big Bang and its evolving complexities. It might be time to reassess the Big Bang theory itself, especially since its depiction has been oversimplified by the public. The Big Bang was not just an explosion occurring within pre-existing space. It marked the very birth of space itself, unfolding around 13.8 billion years ago alongside matter and time. A central idea in modern cosmology is that of a singularity, a point where gravity becomes so extreme that the fabric of spacetime becomes infinite. After billions of years since the universe's inception, it has become clear that our cosmic home is part of a much larger system. For scientists, this discovery has provided an essential aspect of the universe's ongoing expansion, suggesting that space itself continues to grow, contrary to past theories that implied otherwise. It is believed that the first stars began to illuminate the cosmos about 200 to 300 million years after the Big Bang, signaling the end of the universe's so-called dark age, when the first bright celestial bodies formed and began to evolve into galaxies. Nevertheless, the pace at which these galaxies developed remains an enigma. A groundbreaking moment occurred on July 22 when the James Webb Space Telescope unveiled its first batch of images, showcasing several galaxies, some of which had already existed roughly 300 million years after the universe's creation. These galaxies, though younger than those observed today, were smaller and less massive, aligning with the scientific models of the time. In the early universe, the matter density was too low to create galaxies as massive as those we observe now. This revelation began with the detection of 6 distinct redshifted bright spots, igniting one of the most significant cosmic puzzles in recent history. These newly identified galaxies, despite their youth, appeared nearly as large as our own Milky Way, sparking intrigue among researchers in the field of Big Bang cosmology. When scientists examined a set of images taken by the telescope's near-infrared camera, they confirmed the existence of these distant galaxies. They used redshift data to deduce that the light from these galaxies had traveled for over 1 billion years before reaching Earth. This suggested that these galaxies had formed between 570 and 700 million years after the Big Bang. This remarkable finding calls into question traditional cosmological expectations, which had anticipated much smaller, less developed galaxies at this stage in the universe's timeline. Instead, the James Webb Telescope revealed galaxies nearly as massive as the Milky Way, contradicting these predictions. The stars within these galaxies had already accumulated masses exceeding 10 billion times that of the Sun, with one galaxy potentially exceeding even this threshold. However, whether this hypothesis is entirely accurate is still under discussion. Even if these findings are correct, the mass of the early universe would have been far greater than anticipated, raising the complexity of the situation even further. The discovery of these galaxies represents a serious challenge to almost all traditional cosmological theories. Even if one of these galaxies proves to be accurate, it would necessitate a reevaluation of our assumptions about the early structures of the universe. The matter density in the early universe would need to be substantially higher than initially thought. Another possible explanation is that these galaxies might have formed in ways that are entirely unknown to us. These revelations have raised questions that require a reassessment of the Big Bang theory. Many space scientists have expressed frustration with these discoveries, frequently airing their concerns in scientific journals. Those who question the mainstream theories are often labeled as unorthodox or extreme. However, it is evident that even those who support the Big Bang theory are confronted with unresolved issues. Among these is the fundamental question of how, 13.8 billion years ago, something could come from nothing. Did something truly emerge from nothing, or was there an external catalyst for this event? Did the Big Bang occur randomly, Stephen Hawking famously pointed out that the nature of time itself began with the Big Bang, meaning the event could not have been initiated by something else or triggered externally. Similar doubts surround the uniformity of radiation and matter across the universe. No matter where we look or at what distance, we observe a similar distribution of systems, nebulae, and radiation across the cosmos. Modern scholars often explain this uniformity with the theory of cosmic inflation. However, some experts have expanded on this idea, suggesting that the universe expanded in a more turbulent manner. According to this theory, expansion occurred only in localized regions, like bubbles, while other regions continued to expand endlessly. This model raises the intriguing possibility that other universes might exist within these expanding bubbles, each governed by its own unique set of physical laws. Such a perspective implies that our universe might not represent the entirety of existence, but rather could be part of a far larger and more complex structure. Within this framework, the notion of an eternal cycle of collapse and rebirth for the universe is proposed. This is just one of many cosmological theories, though. For example, a 1955 article in NASA's Big Time magazine proposed that the universe may have never had a Big Bang and might have always existed, possibly for an infinite period. In this interpretation, the universe's expansion would be absent, and the continuous evolution of matter would give the impression of gradual development over time. One particularly captivating theory emerging from quantum physics and string theory suggests that our universe might be a projection or simulation originating from a higher dimensional reality. While this might seem like the plot of a science fiction story, it connects to the concept of the Kardashev scale, which measures a civilization's ability to harness the energy of an entire galaxy. A Type 3 civilization capable of using the energy of a galaxy might be able to create a perfect simulation of a universe. However, proving the validity of such a scenario remains an enormous challenge. Exploring the depths of cosmology and the origins of the universe leads us into a world of great mystery and continuing scientific inquiry. The new imagery from the James Webb Space Telescope has reignited debates about the fundamental fabric of existence, forcing scientists to test established theories and reconsider essential concepts regarding the cosmos. At the heart of this discussion lies the theory of the universe's origin, which serves as the foundation of modern cosmology. According to this theory, approximately 13.8 billion years ago, the universe emerged from a hot, dense state, rapidly expanding and giving rise to the space-time and matter we see today. This monumental event wasn't just an explosion within pre-existing space, but also marked the creation of space itself. The concept of a singularity, where gravitational forces become so intense that space-time curvature becomes infinite, supports our understanding of the early universe. However, the discovery of large, mature galaxies a few hundred million years after the Big Bang challenges the traditional ideas of how quickly early cosmic structures could have formed. These findings imply that the early universe had a far higher density of matter than previously assumed, which raises significant questions about how such large structures could have emerged so rapidly. This forces cosmologists to reconsider how galaxies like those observed by the James Webb Space Telescope could have formed so early in the universe's history. One key theory impacted by these discoveries is cosmic inflation, which posits that the universe expanded exponentially in the moments following the Big Bang. This rapid inflation is thought to explain the uniformity of the cosmic microwave background radiation we see across the universe today. However, the latest revelations are introducing complications that may require adjustments to our understanding of inflation. The formation of these large, early galaxies also raises essential questions about dark matter and dark energy, two enigmatic components that make up most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework for galaxies to form, scientists still lack a clear understanding of its distribution and properties in the early universe. In response to these unresolved mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang theory. Some of these models suggest that our universe could be one of many within a vast multiverse, each governed by its own physical laws and constants. These concepts, which stem from string theory and quantum cosmology, propose a far more intricate and interconnected cosmos than previously imagined. One increasingly popular theory is the concept of time inflation, in which universes continuously emerge within a larger, ever-expanding space. This suggests that our universe might be just one bubble among many, each with its distinct physical properties. The challenge, however, is finding observational evidence to support these speculative ideas, as they push the boundaries of what can be scientifically tested. Another provocative theory posits that our universe might be a computer-generated simulation, drawing parallels to advancements in artificial intelligence and computational science, where simulations can recreate complex systems. If this theory is true, it would radically alter our understanding of reality and spark profound philosophical and scientific debates about the nature of existence itself. As observational astronomy continues to evolve, instruments like the James Webb Space Telescope, with its unmatched sensitivity and resolution, promise to uncover even more of the universe's secrets. Future observations may provide deeper insights into the earliest moments of the cosmos, potentially revealing clues about its ultimate fate and the fundamental principles governing its ongoing evolution. Meanwhile, particle physicists remain dedicated to uncovering the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a primary goal in theoretical physics. In the realm of quantum mechanics, debates over the nature of time continue, with some theories proposing that time itself might be evolving or even changing at the most fundamental levels. Understanding the nature of time in the context of cosmology could revolutionize our comprehension of the universe's origins and its ongoing development. Additionally, the search for extraterrestrial life continues to captivate both public interest and scientific research. The discovery of exoplanets, planets orbiting stars outside our solar system, has broadened our understanding of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could reveal biosignatures indicating the presence of life beyond our planet. As scientific exploration progresses, so too does the philosophical inquiry into humanity's place in the universe. The search for answers to questions about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will continue to shape discussions in both scientific and philosophical circles. As we push the boundaries of scientific exploration, we find ourselves standing at the crossroads of new discoveries and long-established theories that are being put to the test. The growing body of data from instruments like the James Webb Space Telescope is revealing a universe far more complex than we had ever imagined. Each new revelation forces us to confront the limitations of our current understanding and pushes us to reconsider fundamental concepts, from the origins of the cosmos to the very nature of existence. These new images are not simply adding layers to our existing knowledge. They are reshaping our approach to the core questions that have challenged scientists for centuries. The James Webb Space Telescope's images have ignited widespread discussions, particularly about how galaxies formed in the early universe. The question of how galaxies could form so quickly after the Big Bang is now one of the most pressing issues facing cosmologists. The early universe, as depicted by current models, should have been far less capable of producing large, mature galaxies so soon after its inception. However, these new findings suggest that the formation of large galaxies may have occurred at a much faster rate than originally believed. One of the critical issues raised by these discoveries is the nature of cosmic inflation, a theory central to our understanding of the early universe. According to this theory, the universe underwent an extremely rapid expansion right after the Big Bang. This expansion is thought to have helped explain the uniformity of the cosmos and the smooth distribution of matter. However, the detection of large, developed galaxies at such an early stage challenges the idea that the universe expanded uniformly across all regions. This discrepancy suggests there may have been far more complexity in the early universe than current models can account for. As scientists continue to analyze the data from the James Webb Space Telescope, they are reconsidering the role of dark matter and dark energy in the formation of these early galaxies. Dark matter, which is believed to provide the gravitational framework for galaxies, has long been mysterious. Its exact properties and distribution in the early universe remain elusive. These new findings could provide key insights into some of these unanswered questions. Similarly, dark energy, which is thought to drive the accelerated expansion of the universe, is another factor that scientists are now beginning to explore more deeply in light of these new discoveries. The implications of these findings go beyond our understanding of galaxy formation, challenging the very structure of our cosmological models and urging us to ask deeper questions about the universe itself. How did the universe evolve from the chaotic and dense state of the Big Bang to the organized structures we observe today? What role did dark matter and dark energy play in this transformation? And most importantly, what do these discoveries tell us about the future of the cosmos?